In section 8.1, we really were given a bunch of similar triangles, and then we were shown how to use the fact that they're similar to identify missing side lengths. In 8.2, we realized that, okay, we were given two shapes that we didn't know were similar, and we started trying to prove they were similar. Because once again, once we know they're similar, we can apply proportional math and other things to find missing parts. And so 8.3 continues that, where we're going to try to prove triangles are similar, and therefore, once we know they're similar, we can find the missing pieces. The first theorem in 8.3 that we're going to discuss is the side-side-side similarity theorem. And it basically says that if the corresponding side lengths of two triangles are proportional, then the triangles are similar. So in this, what we have to do is we have to create a scale factor for two of the sides. And for this one, I'll do, let's say, small over big. That's how I'm going to set it up so I'm consistent. And I see that AB goes with DE. So AB and DE go together. So I'll do 4 over 8. And I realize that the scale factor is 1 to 2. Well, if these triangles are similar, then when I do BC and EF, that's down here, those two sides are going to have the same proportion. So again, I'll do the small one over the big one, and notice that I got a half, so that looks good. And then I'll do the third pair of sides, AC and DF, which are these two. And again, I'll do small over big, and I get 1/2. And because all three of them simplified to the same ratio, 1/2, I know that these two triangles are similar using side-side-side similarity theorem. So the third method we're going to use to prove that two triangles are similar is side angle side. And although you can't see it in this picture, this angle here is equivalent to this angle there. They're congruent, and the tick marks are just, or the arc marks are just hidden. So if we can prove that two angles are congruent and the sides that include that angle are proportionally similar, then we can prove that the triangles are similar. So what do we mean by the sides that include the angle? Well, that angle is formed by these two lines and these two. And if you notice, the angle is included in them. In other words, those two sides make that angle. So if we can prove that AB and DE have a particular scale factor, I'll do small over big, right? So I'm going to do DE over AB, and that's 4 over 8, which is 1/2. If that ratio matches DF over AC, which is 5 over 10, which is also 1/2, notice those two sides are proportionally similar. And so I have two sides that are proportionally similar, and I have an included angle, angle A and angle D, are congruent. Then I can prove using side angle side similarity that these two triangles are similar. And what that's going to tell me, and what I'm going to know by that, is that if those two triangles are similar, I know that angle C is going to be congruent to F. I know that B is going to be congruent to E. And I know that this third side, BC and EF, are going to have the same proportional relationship as do the other two pairs of sides. So just to review what we talked about, the three theorems that we've done in, or postulates theorems that we've done in 8.2 and 8.3, is again that if we know that two angles in one triangle are congruent with two angles in another, we know the triangles are similar because of angle-angle similarity postulate. We know that if three pairs of sides have the same scale factor or proportional relationship, we know that the triangles are similar using side-side-side similarity theorem. And again, we know that if we can prove that two sides have the same proportional relationship and the included angle is congruent, we know that side angle side similarity theorem proves that the triangles are similar. So now let's work some problems out where you actually have to apply those theorems. So notice it says the measure of sides of triangle ABC. So let me do ABC. Here's triangle ABC. And let's do a bigger triangle, X, Y, and Z. It says the sides are 4, 5, and 7. So let's just do 4, 5, and 7, and let's do that same order, 16, 20, and 28. And they want to know if the triangles are similar. Well, notice that we haven't been given any angles, and so angle, angle is out, and side, angle, side is out. However, what about side, side, side similarity? So what I'm going to do is I'm going to take two sides, 4 and 16, and I found their ratio is 1/4. Now I'm going to take 5 and 20, and that should give me the same 1/4 if the triangles are similar. And I'll take 7 and 28, and that should give me the same ratio. Notice I got 1/4 for every single one, which means the sides are proportionally the same, and therefore the triangles are similar because of side, side, side similarity theorem. In the second example, it says in triangle ABC, so let me go over here again. Let me do A, B, and C. And then again, I've got X, Y, Z, which appears to be a little bit bigger. And it says that AB is 2, AC is 5, and BC is 6. In XYZ, it says that XY is 2.5. It says that YZ is 2. And it says that XZ is 3. Okay? And it wants to know, is ABC similar to XYZ? So again, you're going to have to come up with your proportions, right? So I'll start with 2 over 2.5. Now this without a calculator is a little hard. I multiply both by 10 and I get 20 over 25. And then now I can simplify much easier. So both are divisible by 5 and I get 4/5. So that's my first pair of sides. That's the relationship between AB and XY. So now I'm going to try to do another set of relationships. I'm going to do BC and ZY. So BC over ZY is going to be 6 over 2 or 3 over 1. And if you notice, this is not equal to that. And so these are not similar because the sides are not proportionally equal. So when it comes to this problem here, it's very complicated looking. And so they're basically telling you that two triangles are similar, and then they're asking you if two other triangles here, can we therefore conclude that they're similar as well? So the first thing I think when you have these types of problems where you have, you know, here's triangle XCP, and then here is triangle XYQ. And so for me, when you see triangles within triangles, it's a little bit confusing, and so I suggest that you kind of take them out. On Notability, this is a really easy thing to do, but then here you've got your this one, and that's might be a little bit hard to see. Let me do that in black. And that's going to be X and P and Z. And so they basically told us that those two triangles were similar, which again tells us that angle X and angle X are congruent, angle Y and angle Z would be congruent, and Q would correspond with P. So now let's talk about those sides then. And we know then that, first of all, they tell us the shapes are similar. They don't tell us that the two triangles are congruent. So even though they look like they're equal size, let's just assume one is a little bit bigger or smaller than the other one, right? So let's give some values to this. Let's come up with a proportional relationship. We can really actually create our own. So let's say, for example, that XP here, this distance here, is 2. And let's make XQ the corresponding one on the other triangle, let's make that 4. So that way we have a ratio of 2 to 4 or 1 to 2, right? So our scale factor that we're going to use for our proportions is going to be 1 to 2. And so let's just make up values for these sides, right? So let's then say that, let's make XC, let's say that this is 6. And therefore, we know that if this is 6, then we know that this is going to be 12. Because again, it's going to have that relationship. Notice that it's double, or if I go this way, notice that it's half, right? So if this is 12, the other side is 6. And then we'll do it with this one here. We'll make this one 8, and we'll make this one 4. Okay, so we come up with these lengths which are proportionally equal. So again, we've got 2 and 4. We've got XY we concluded was, let's say, 12. And we have XZ, which we drew out, and we got 6 for it. Okay, and then we also have these lengths here where we have PZ is 4, right? And then QY is 8, right? So the green one is 8 and 4, but those middle ones aren't going to matter. So I'm going to leave them out of this drawing. They just serve to kind of confuse. So what's going to happen now is I'm going to, now that I kind of came up with these make-believe values, but because they're all proportionally equal and the shapes are similar, this is a valid method of, trying to solve this particular problem. So now that I have these, they're asking me, does it follow that triangle XPQ, again, triangle XPQ is this top one, so I'm going to write it here, XPQ, and I already know that this is 2 and this is 4, right? And they're asking me if it is similar to XZY, and XZY would be, notice, this large outer triangle. So X, Z, and Y. Now I have to be careful here if you notice, because it did say P goes with Z here. So since P is here, here's Z and here's Y. And it is kind of flipped from this version. Notice this is Y and Z, so it's kind of flipped over. So I have to be pretty careful when I'm wondering about that, right? So let's see if that's going to make a difference, right? So I know X to Y, right? XY here is 12 units, and I know that XZ here is 6 units. Okay, so again, I now have to ask myself, is this new pair of triangles similar? Well, angle similarity would require that I prove that 2 angles are equal, and unfortunately, I only can prove that 1 angle is equal. Angle X equals angle X. So I can't use angle, that's out, right? The next one is side, and the issue that I have there is that I don't know this side or this side, so I can't prove that they're proportional. I have 2 pairs of sides, but I don't have the third side, so that one's out. So side, angle, side is going to be the one that if I can prove these to be similar, that's the one I'm going to need to use. And so what I do here is I say, okay, are the sides proportionally similar? What is the ratio of 2 to 6? Well, that's 1/3. That works. What is the ratio of 4 to 12? That's also 1/3. And so notice that 2 sides are proportionally equal. And the included angle is X, which means that is congruent. And so yes, I can conclude that this pair of triangles is similar using side angle side similarity theorem. So had I not come up with the values, had I not come up with these practice numbers and create a relationship that was proportionally equal, I would not have been able to have solved this. But because I did, I was able to solve it. And so yes, you can insert numbers to reason something out logically. And in this last one, we're just going to name similar triangles and give the postulate or theorem. So the postulate would be angle, angle, and the theorem would be side, 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 or side, angle, side. So when I look at this one, notice that this angle here is equal to this angle here, right? And I know that angle A equals angle A, it equals itself. So I know that triangle ADE is going to be similar to triangle ABC because of angle, angle postulate. When I go to B, I'm going to work on, for example, I see, we're talking about triangle CDE, right? And we're comparing it to triangle CAB. And I know that angle C equals angle C. That makes sense. Now, let me find the proportion, let's say, of the small side to this big side, right? So I've got 6/9, which is 2/3. And then I do this small right side, 10/15, which is also 2/3. And so I see that my sides have proportionality there as well. So I know they're similar because of side angle side theorem, similarity theorem. Again, I proved that the two sides and the included angle, the two sides are proportionally equal and the included angle is congruent. So that's that one. And then the last one we're going to work on right now is C. And we have these two triangles here. And what we need to do with these triangles is figure out what are the corresponding parts and the order, right? And so what I'm going to do is I'm going to match them by side length smallest to biggest. And I realize that KL is the smallest side and KL matches with KO. Okay? Then we go to the medium side, which is going to be LM, and that also matches with ON, so LM and ON. And then the largest pair of sides is going to be MK and NK. So if those three sides have the same proportion, then I know that my triangles are similar. So KL is 3 and KO is 6, which is 1/6, 1/2. Well, that looks good, right? Then I go to LM, that's 5. I go to ON, that's 10, and notice that's also 1/2. So far, so good. Then I go to MK, which is 6, and NK, which is 6 plus 6, right, is 12. And that's also 1/2. And I realize, yeah, all three sides have the same ratio of 1/2. And so, yes, my triangles are similar using SSS similarity theorem. And if I ask you to name the triangles, then you would say triangle KLM is similar to triangle KON. And that's it. So just remember, there's 3 ways to prove triangles are similar if it's not given to you initially, and it's angle, angle postulate, side, side, side theorem, or side, angle, side theorem.